everyone. Today we are going to deal with some of the mathematical logic part 3. In this we are going to learn about predicates, existential and universal quantifiers, and definitions and proof of the theorems. Then what do you mean by predicate? Predicate is a declarative sentence which contains one or more variables and is not a preposition basically. But if you replace variables in the predicate with some certain allowable values, then the predicate becomes the preposition. So predicate logic is an extension of prepositional logic. It permits concisely reasoning about whole class of entity. How we can represent a predicate? The predicate is represented with letters, capital letters P. Here we can say, if you consider P as a predicate which contains the variable like x1, x2, x3, so on up to xn, where n is greater than or equal to 0, which can be mapped from some set of domains to values true and false. In other words, if you replace x1, x2, xn by instance in their corresponding domains, we will get a preposition. Here is an example. Here P and Q are the two predicates. The predicate P contains the two variables x and y, that is x is greater than or equal to y raised to 2. Where the domain of x and y is equal to natural number. Similarly for Q also, there is a set of names father, son, cat and dogs. If you replace here x and y values, then this Q becomes a preposition. Next is domain. As I said, the predicate contains the variable. These variable will take some set of values from certain domains to become a prepositions. Let's consider P x1, x2 up to xn, where x is greater than or equal to 0 be a predicate. Then a set of domain like dx1, dx2, dx3, so on up to dx is called a domain of a predicate P. Next, truth set. As I said, as in the case of prepositional logic, every preposition has a truth and truth value that is either true or false. Similarly, the predicate will become a preposition by replacing the x value from the certain allowable values in the domain, so that it will become a preposition. So every predicate has a truth set. Here we can represent the truth set for the predicate P as Tp is a subset of dx1, dx2, dx3, so on up to dxn, such that for all a1, a2 up to an, which are subset of Tp, and here if you replace x with a, then which gives some set of some truth set. It may be either true or false. Here example, we need to identify which are the predicate and which are not predicates. Here if you replace the domain of x is R here, if you replace x here with any value of R, then this predicate become a preposition which results either in true or false. According to the definition of predicate, 1, 2, 4 and 5 are the predicate, and 3 and 6 are not predicates. Then some important terms we can see here. The open sentence means any declarative statement. Here if you consider x plus 3 is equal to 6, x divides 4. These sentences are not preposition unless if you replace the symbol x with a specified value, and this kind of statements are called open statements or open sentences. Free variable, unspecified symbols such as x in an open statement is called free variable. Then inverse or inverse of discourse. Here the domain of unspecified symbol x in an open sentence is called inverse or inverse of discourse. And that means the inverse of discourse is nothing but domain for the unspecified symbol x. Open statement containing the variable x denoted by p of x, q of x, etc. If u is a inverse of discourse, for the variable x in open statement p of x and is a is a subset of u, then the preposition got replaced, x by a in p of x is denoted by p of a. Next is quantifier. Quantifier means in the preposition the words like all, for every, some, there exist such type of values which are associated with the idea of quantity. Such words are called quantifiers. We have two types of quantifiers, that is universal quantifier and existential quantifier. First we'll see what is universal quantifier. The symbol for representing universal quantifier is for all. This is a symbol which we can read it as a for all, for each, for any and for every. Such quantifiers are universal quantifiers. Let's consider q of x is a predicate. The x contain the D is a domain for x. Then universal statement is a statement of the form for all x belongs to D. Q of x is defined to be true if and only if q of x is true for every x in D, and it is defined to be false if and only if q of x is false for at least one x in D is false. Okay. For example, here we can express the sentence all human beings are mortal as for all, this is a symbol, human beings is represented as x, so x is mortal. Next, second type of quantifier is existential quantifier, is represented with a symbol this one, and you can read it as a there exist, which represents some words like for there exist, for some, for at least one, and are called existential quantifiers. Let q of x be a predicate, be the domain of x, then existential statement is a statement of the form there exists x belongs to D such that q of x is defined to be true if and only if q of x is true for at least one x in D, otherwise it is false. Example, there exists m belongs to Z such that m square is equal to m. Next, some important terms we can see here, that is quantified statement. The statement, quantified statement means a preposition involving universal or existential quantifiers are called quantified statement. Quantified statement is a preposition of the form for all x belongs to S p of x, or there exists a x belongs to S p of x, where p of x is an open statement, S is a universe for x in p of x, or you can say domain of x in p of x. Bound variable, the variables present in the quantified statement are called bound variable, and they are also called bound by the quantifiers. Truth value of the quantified statement, the following we can see by seeing the rules we can identify what is the truth value for a given quantified statement. First rule is the statement for all x belongs to S, p of x is true only when p of x is true for each x belongs to S. That means if there are 10 values, for all the 10 values p of x should be true. Okay. Second one is if the statement there exists x belongs to S, p of x is false only when p of x is false for every x belongs to S. That means if you identify one element which is false, then the p of x will become a false statement, or the truth value of the quantified statement is false. Counter example, to infer that the preposition of the form for all x belongs to S, p of x is false, it is enough to exhibit one element of S such that p of A is false. This is called counter example. That means if you want to prove it as a false, then you can select any value. If for that value the truth value becomes false, then the complete quantified statement becomes false. Next, there are two rules for inference in the case of quantified statement. That is, if an open statement P of x is to be true for all x in the inverse of S, then A belongs to S, then P of A is true. This is called rule of specification. That means if you consider any value in S, if it is true, then it is called universal specification. If the open statement P of x is to be true, if for any x chosen from the set S, then the quantified statement for all x belongs to S, P of x is true, then it is a rule of generalization. Okay. Next is logical equivalence. These are the sum of the values which are logically equivalent to each other. That means the truth value of this quantified statement is same as truth value of this quantified statement. Here that is for all x, P of x and Q of x is logically equivalent to for all x, P of x and for all x, P, Q of x. Then there exists a x, P of x or Q of x are is logically equal to there exists a x in P of x or there exists a x in Q of x. Third one is there exists x, P of x implies Q of x is logically equivalent to there exists x negation of P of x, negation of P of x or Q of x. These are some examples. Here for an inverse of all integer, that is domain is set of all integer, P of x, x is greater than 0 and Q of x, x is a even number. Write down the quantified statement in a symbolic form. They have asked at least one integer is even, at least represent what? There exists x is even, x is even, it is a preposition Q, predicate Q or open statement Q, so we can represent it as there exists x in Q. There exists a positive integer that is even, that means again here there exists, the symbol is there exists, the positive integer, that means it should be greater than 0, so it is P of x, and that is even means it should be positive as well as it is even means P of x and Q of x. Similarly, we need to find the truth value here. Here if you replace x with 2, 2 is not greater than 3, so it will become a false. Truth value of first statement is false. Then if you consider P of 3 is not greater than 3, so the P of 3 is false, or negation of P of 3, negation 3 plus 1 is 4 is even, but negation of this is 4 is not even, that is false. That is the false and true is true, so truth value is true here. Next is logical connectives for the quantified statement. As we in the case of compound open statements, they can be formed by using the logical connectives. Here also we can form the open statements, compound open statement by using the logical connectives. Such logical connectives are similar to normal preposition connectives like negation, conjunction, disjunction, conditional and biconditional. We can have a similar truth table here also. The negation of P of x is denoted by this one, and truth table, if P of x is true, then negation of P of x is false. If P of x is false, negation of P of x is true. Similarly for conjunction, if we have a open statement P of x and Q of x, then P of x conjunction Q of x for the open statement P of x and Q of x. This is a truth table. Only when both the open statements truth value is true, then the result is true, otherwise in all other cases it is false. Same as disjunction here. In this, we can see the truth value when both the input open statements truth value is false, then the result will be false. In all other cases it is true. Conditional, if P implies Q, it is represented as P implies Q. when the first open statement is true and second open statement is false, then only the result will be false. In all other cases it is true. In case of biconditional, this is called double implication, or it is called biconditional. In this case, P of x, if both the inputs are not same, truth value of both the inputs are not same, then the result will be false. In all other cases it is true. Example, here we need to find the truth value for the open statement. Same here, P of x is less than or equal to 3. If you replace x with 2, then it will become preposition. Then 2 is less than or equal to, which is true. So the compound preposition, this open statement is true. Similarly, for q, negation of q, we have to find here 4 plus 1 is odd. 4 plus 1 is 5. 5 is odd. Negation of this is 5 is even, which is false. Same as here, we can use a logical connective and use ಮಾಡಿರೋದು. P of minus 1 is preposition, minus 1 is less than or equal to 3, which is true, and q of 1 is preposition is odd, which is false. Therefore, the P of minus 1 and q and q of 1 is false. Next is negation of quantified statement. Already you know what is quantified statement. Here we can determine the negation of quantified statement. Statements forms an important part of the logical argument. The following are the rules for negation for the quantified statements are: first one, to construct the negation of quantified statement, change the quantifiers from universal to existential or vice versa. That means if there is a universal quantifier, then change it to existential. If it is a existential, then it should be universal. And also replace the open statement by its negation. Let's consider example, negation of this quantified statement for all. This is a universal statement. This has to be changed to existential statement with a negation of open statement. Similarly, here it is a existential statement that has to be changed to universal statement, and you have to make this open statement as negation. Okay, here is an example how to make a negation. Just here we have to replace what we need to replace. There exists has to be replaced by for all, and the negation of P of x and negation of or q of x. By using the De Morgan's law, you can change it to negation of P and negation of q. Okay, this is also similar kind. Just remember, replace there exist by for all has to be replaced with there exist, and we need to make the open statement into negation of that statement. Okay, next is definition of proof. A proof is a valid argument that establishes the truth value of a truth of a mathematical statement. Proof is a valid argument basically which establishes the truth of the mathematical statement. There are two types of proof. First one is where all the steps are first one is a formal proof where all the steps are supplied and the rule for each steps in the arguments are given. Okay, in informal rule where more than one rule of inference may be used in each step, where the step may be skipped, where axioms being assumed and rule of inference are used are not explicitly stated. Okay, these are the types of proofs. We have totally 5 types of proofs. One is direct, indirect, proof by contradiction, proof by exhaustion, and proof by existence. First one, direct proof. In this case, conditional statement P implies Q is constructed when first step is assumption that P is true, subsequent step is constructed using the rule of inference with the final step showing that Q must be true. The direct proof shows that conditional statement P implies Q is true by showing that P is true, then Q must be true. In the direct proof, we assume that P is true and use an axioms, definitions, and previously proven theorem together with the rules of inference to show that Q must be true. Let's consider here is an example. Give a direct proof of a theorem if n is an odd integer, then n square must be odd. Okay, consider any number like 3 square, 3 is odd number, 3 square is 9 is again odd number. That we need to prove it by direct proof, that we assume that n is odd. This is a hypothesis that is given here, and we can make it as the definition for odd number is 2k plus 1, where k is some integer, a definition of odd number. And we can square on both sides, it will be n square, 2k plus 1 whole square, it will become, by expanding this one, it will be 4k square plus 4k plus 1. Here we can take 2 common in both the factors, 2, then 2k square plus 2k plus 1 by using squaring method. Then since r is equal to 2k square plus 2k is an integer, okay, then n square is equal to 2r plus 1. Any number with the plus 1 is equal to odd. So it is the proof by direct method. Next is proof, indirect proof. In this indirect proof, we'll consider the contrapositive of the condition here. P implies Q and its contrapositive is negation of Q implies negation of P, which are logically equivalent. We already knew it. In some situation, given a conditional P implies Q, a direct proof of the contrapositive negation of P implies negation of Q is easier. On the basis of this, we infer the conditional P implies Q is true. That means we have to prove here Q contrapositive of the conditional is true. Then we can say that the P conditional is true. This method is called indirect method of proof. In this, the proof that P implies Q is true, that precedes by showing the P must be false when Q is false, and it is proving that the conditional statement P implies Q by showing its contrapositive negation of Q implies negation of P is true. Let's consider here example. 3n plus 2 is an odd integer, then n is odd. Assume that contrapositive we have to consider here, n is even number if you take, okay, then this implies n is equal to 2k for some integer according to the definition of even numbers. Then what happens here, 3n plus 2 is equal to 3, n is replaced by 2k here plus 2. 3 into 2k is 6k plus 2. If you take 2 common, then 3k plus 1. Any number which is multiplied by 2, then it will become a even number, since the negation of the conclusion implies that negation of the hypothesis. So the original conditional is true. Next, proof by contradiction. The indirect method of proof is equivalent to what we know as proof of contradiction. The line of argument in this method is to prove the P implies Q as follows. Hypothesis, we have to have here P implies Q is false. We assume that P is true, Q is false. Then analysis, starting with the hypothesis that Q is false, employing the rules of logic and other facts, infer P is false. this is contradictory to the our assumption. So conclusion will be what we infer that P implies Q is true. Same example you consider here. Assume that the given statement is false and assume ಮಾಡ್ಕೊಳ್ಳಿ. Then when we have 3n plus 2 is odd, then n is even, negation of that, then which implies again the same thing, n is equal to 2k for some values, then 3n plus 2 is equal to 3 into 2k, that is equal to, we take 2 a common, any number multiplied with 2 is again even. This contradiction occurs, so the original statement is true. Next is proof by exertion. Proof by exertion, in this we can say the proposition of the form for all x belongs to S, P of x is true if P is true for every x in S, if S consists of only a limited number of elements. We can prove that the statement for all x belongs to S, P of x is true by considering P of A. For each A in S, verifying that P of A is true. This method of proof is called method of exhaustion. Let's consider here we have a range for n, that is n should be, n lies between 2 and 26. We can write up the sum of at most 3 perfect square. Okay, we have a limited number according to the definition of proof by exhaustion. The S should be limited, so we have only the number from 2 to 26. We have to prove that the statement for all x belongs to S, P of x is true, where P of x is, we can define it as a x is a sum of at most 3 perfect squares. We observe the following. Consider 2, 1 square plus 1 square, again it is 2. 4 is equal to 2 square. 2 square is equal to 4. 6 we can interpret as 2 square plus 1 square plus 1 square. The above facts verify that each x in S is the sum of at most 3 perfect squares. This establishes the required result. The last method is proof of existence. In this case, there exists x which belongs to S, P of x is true if any one element A belongs to S such that P of A is true is exhibited. Hence, the best way of proving this proposition, there exists x belongs to S, P of x is to exhibit the existence of one element A which belongs to A. For that, P of A is true. This is called proof of existence. Here we can prove there exists a positive integer m and n such that m, n and m plus n all are perfect square. Note that if consider a value m as 9, n as 16, which are already perfect square. If we add m plus n, that is 9 plus 16, which is equal to 25, again 25 is a perfect square. According to this, according to the proof of existence, we can prove the above result. For more information and examples, you can refer these books. Thank you.